Thank you, Professor. So the title of my presentation is Risk Assessment of Quarry Activities on Groundwater Resources. First, I have to say that there is no quarry activities into urban area. So, of course, the topics of my presentation will mainly be in relation with the thematic of support for management and effective protection of groundwater. Okay, quarry sites in Belgium, the quarry activity are still quite important in Belgium. You can see that every year the extraction rate is about 63 million tons in 2011. So you should say that for 1 ton, the price is about minimum €5 per ton. So you can see that it's quite, it's still a good industrial activities. On this map, you have the location of the different sites with the importance of the different quarry. This is the different material which is used by the quarry, and immediately you can see that the majority of these quarries are located in aquifer. 73% of them are located in aquifer, 7% in aquator, and 20% in aquicute. So this is the proportion of each quarry site. But now, if we look to the material, the vision is a little bit different, because you can see that all the material are generally aquifers. They are so located, you can see limestone, chalks, not porphyry, but sandstones and sands. That's the majority of the material that are extracted by the quarry activity. So you can see that about 98% of this material consists of aquifer formation, which is very important. So now when you look, of course, when you make the comparison between the two maps, the first one with the quarry site location map, the other one, the water catchment location map for the water supply mainly for the population, you can see, of course, that there is a close relation between the location of the quarry and the location of the groundwater catchment. So, of course, there is some competition between the exploitation of the stone and the exploitation of the groundwater. So, for an example, this is an area in Belgium. This is it's the city of Soigny. It's 26,000 inhabitants. The altitude of the town is 90 meters above sea level, and the water table is about 10 meters deep. So the water table is about 80 meters above the altitude. In this area, we have 3 main quarry sites, which exploit some limestone formation, and of course, each of the quarry, the bottom, the base level of the quarry, it's below the water table. You can see for this one, the altitude is 38, minus 10 meters below sea level, and 25 meters. Of course, as soon as we are in aquifer formation, limestone formation, as soon as the quarry level is going down the water table, they have to make some dewatering. So you have here the volume and the number of million cubic meter per year for each quarry, and you can see that the total volume for these 3 quarries is about 9 million cubic meter per year. That means more or less 400 cubic meter per hour. So you can see that it's quite an important amount of water, and generally this water is through to the surface water system. So in fact, dewatering activities due to quarry activities, 2 problems for the quarry and for the producer himself. So that means extra production cost, because dewatering needs a lot of money for only electricity. Sometimes it lead to technical difficulties, and also you should know that they have to pay taxes on the dewatering volume, which is about €0.07 per cubic meter. For the government, there is a problem with this dewatering system in terms of water quality stress on the aquifer, but also on the water, of course, quantity stress on the groundwater resources. So due to this situation, the Walloon government, which is in charge of the management of the groundwater resources, asked us to start a project which is called Risk Assessment of Quarry Activity on Groundwater Resources. So it's funded by the Walloon region, and when we have this kind of project with the Walloon region, of course, we have some people from the water supply company, which is called Aquawal, which is a confederation of water production company. The FEDEX is the federation of the quarry company. This is generally the federation for the big company, generally international company, and we have also a federation of the more local companies. So the first objective of the project, of course, as any kind of hydrogeological investigation, is to make a description of the hydrogeological context for each quarry site. And the second objective is to try to have an estimation of the dewatering impact on groundwater resources. So you can see here some flow, which is due to the depth of the quarry, which is below the groundwater table, and you can see it's a dolomite formation, and you can see the water which has to be pumped for the dewatering system. And generally, the water flow on the bottom of the quarry where they have some pump to pump the water to the surface water systems. So the first problem, but it's for every hydrogeological investigation, it's how to assess hydrogeological impact of the dewatering. As hydrogeologists, everybody knows the way to proceed. We have to start with geomorphological context, geological characterization for each site, hydrogeological characterization again for each site, and then maybe, if we have time and the money, we can make groundwater models. So, for example, I'm going to take the example of a quarry which is owned by the Rust industry. Rust industry is the world leader in lime production, and they have a big quarry located between the city of Namur and the city of Ardennes. And this quarry is close to a main river of Belgium, which is called the River Meuse. So if we look to the site, you have here the River Meuse, you have the quarry site, and here is the factories. So you can see the quarry is subdivided in two parts, because in the middle they have a small stream. So this is the first step, is the geomorphological investigation. So you can see two quarries separated by a small river. In blue, that's the location of this small river, which is called Namur River. The main river of this area, which is the regional aquifer base level, is the River Meuse, and the altitude of the River Meuse is about 75 meters above sea level, and presently the quarry flow is about 35 meters above sea level, so that's mean 40 meters deeper than the River Meuse. So this is for the geomorphology. For the geology, you can see the geological map with different cross-section. So from the north to the south, we have all the rocks which are sandstone, Familian sandstone. Then we have here a small formation which consists of shale formation. Then here we have Tournesian dolomite, and in the south parts of the area it's Tournesian limestone. The production, the quarry mainly use the dolomite formation. If you look to the cross-section, I'm going to show you this cross-section, so D prim. So this is the cross-section. In yellow, this is the base of the region which consists of Familian sandstone, the impermeable layer of clay, and in green, this is the dolomite. So you can see the level of the Meuse, River Meuse, altitude 75 meters, and this is the lower flow of the quarry, which is at the altitude of 35 meters. So of course, as dolomite are very permeable, we have seen the pictures before, with all this groundwater flow, the company should make some dewatering. Fortunately, for the hydrogeological context, this is a big company, so we are quite lucky to have some historical data. So we were able to draw the natural piezometric map according to the data they have collected in 1995, and we can make also some more recent piezometric map according to the present situation. For the present situation, you can see the modification of the piezometry, and of course they have to compute the dewatering, the volume of the dewatering, and the dewatering now it's about 650 cubic meter per hour, on which of course they have to pay the taxes. So using the data, we can see the evolution of the dewatering volume. This is the blue lines. This is due to the precipitation, and the dark blue lines is mainly due to the volume of water which flow from, of course, the river Meuse, which is constant height in terms of modeling. And you can see that the level here is the flow 7. The flow 8 is the deepest one with the altitude of 35 meters. So you see that in 2005 they reach the present altitude, 35 meters, but you can see two steps in the dewatering. The first one, and then you see that more recently, even if the flow level didn't move down, the dewatering volume increased. This is simply due, this is also another way to see the bar show the amount of the dewatering, the discharge of the dewatering, and here you can follow the evolution of the piezometry. So while there is a difference in pumping, even if the bottom of the quarry is fixed, it's just because, so in the beginning, the dewatering level is 35 meters. So when they dig from the stage 6 to the stage 8, the discharge increased from 200 to 400 cubic meters per hour. But then, later on, they move laterally in direction of the river Meuse. And as they move laterally, the lateral extension closer to the river Meuse increase the dewatering volume from 400 to 700 cubic meter per hour. So you can see that there are two factors. Of course, the depth of the quarry has a high influence of the dewatering, but also in this situation, the distance between the river Meuse, which is a constant head level, and the location of the quarry itself. And in the future, we make also some modeling to see how the dewatering volume will increase if they move not closer but further the river Meuse, and you can see that the increase of the volume is not very high. So first step, second step, and then when they will move further away than the river Meuse, you can see that the lateral extension further the Meuse will lead to get a dewatering of about 700 cubic meter to only 720 cubic meter per hour. So this information is given, of course, by using a groundwater model. This is roughly, you can see that this is a mud flow model with the number 3, 1, and 2. This is constant height boundary of the model, and the boundary for its impermeable boundaries. So this is, for example, the result of the model. You can see the importance of the groundwater flow into this area, and of course the main groundwater flow comes where the quarry has the shortest distance from the river Meuse. So you can see that this kind of investigation is quite regularly made by hydrogeologists. There is nothing exceptional, except that, of course, you need some information. You need to have some borehole, pumping test. You need to have some piezometric information for the calibration of your groundwater model. More than this, if you have some hydrochemistry information. Of course, it could help you. We also perform some tracer tests in the air. But the problem, such detailed investigation need, of course, numerous data, time-consuming, that's been a lot of money. Also, in the context of our contract with the Walloon region, we have to make the characterization on 156 sites. So the question was, what can we do? Because the conclusion, it's impossible to conduct such investigation into such detail for each of our 156 sites. Could be too detailed also for the administration and decision maker, because in the beginning we start, of course, to make clear description for each query site, and in the end we say, okay, we will have a big final report for about a description of few pages for each of the query, but I'm sure that this report will be never used by the administration and the decision maker. So we try to make maybe something more simple that could be used. The question, how to conduct a first assessment of query-aquifer interaction, how to translate scientific information, detailed hydrogeological information into practical recommendation. So the origin of the methodology we are going to use is based on the well-known risk mapping methodology. You know that risk is equal to probability multiplied by the impact of some events on the population, on an aquifer, and so on. In the case of our study, we can say that the environmental effect or the interaction effect between the quarry and the aquifer is the quarry environment quantification multiplied by the aquifer potential. So how is it work? First, we are going to try to give a characteristic of the quarry environment. For this, there is different situation according mainly, but according, of course, the hydrogeological environment. The quarry is in an aquiclude, an aquitard, an aquifer. You already saw that the majority are located in aquifers, but mainly what is the depth, what is the quarry, the altitude of the quarry flow according to the piezometric level. You can have, you see, different situation. The quarry is above the natural piezometric level. The quarry could influence locally the piezometric level. The quarry could go deep enough that it could have a regional influence. Okay, so first the characterization of the quarry environment. We base our methodology on three simple parameters. The first parameter is the hydrogeological context, which could be an aquiclude, aquitard, aquifer, or even karstic aquifer. For each of these parameters, we give a number, one for aquifer, and of course, 4 for the karstic aquifer. The second information is the second parameter is the geological context, because you can have a karstic aquifer that could be completely isolated by, for example, impermeable formation that exists. For example, in Belgium, we have some old Franian reef, Des Franian reef, which are generally used by quarry people. Because the quality of the limestone is very good. It's mainly almost pure limestone, so pure calcium carbonate, so it could be used to make carbonate lime. So, but these reefs are really located, surrounded by impermeable formation. So the geological context, we say, okay, the quarry could be isolated, partially isolated, with a local extension or a regional extension. The different quarry I show you using the Google pictures in the beginning of my speech, they could be considered as a regional extension. So again, according to the characteristic, we can give a number going from 1 to 4. The last parameter to characterize the quarry environment, it's of course, I explained before, the regional piezometry. The quarry flow is up the aquifer level. The talweg, so the regional base level, is down the quarry flow, but the quarry flow has some influence locally on the piezometric level. And another possibility is that the quarry flow is lower than the regional river, the general base flow, but it's not. But the base flow consists of constant head level. You see, that's the example. Sorry. That's the example of the Machtedam quarry. I explain you. Here you have the Meuse level. So the Meuse level is considered as a constant head. And the worst case, the quarry flow is down the regional base flow level. But you see, here you have infiltration. The rivers are so small that they could not be considered as a constant head boundary. So, as we suppose that this regional piezometer and the influence of the quarry on the piezometry is very important, this parameter was multiplied by a factor of 2. So we have the value of 2, 4, 6, and 8. And then, of course, we had this different parameter, and we have a range for that can, so the number can range from 4 to 16. So this is for the quarry environment. So now we have to characterize the aquifer potential. So first, what is the quality? The quality could be low, medium, or high. For example, we know in Belgium that some aquifer, even if they are used for drinking water, that the quality is not very good because we have some pesticide problem. The water has to be treated before to be distributed. Also, we have some aquifer which has some problem in nitrate concentration. So we can have a rough estimation of the water quality. The water quantity, again, it could be low, medium, or high. For example, even if we have two aquifers, like a sandstone aquifer or a limestone aquifer, it's clear that the potential, the quantity of a limestone aquifer is higher than the quantity that you can pump from a sandstone aquifer. And the third parameter is the characterization of the water catchment according the position, of the quarry according probably water catchment, for the water supply of the population. It's out of the feeding zone, it's in the catchment, or it could be in the protection zone. The Belgium is very dense, has a dense population, and it's also we have quite a lot of water catchment. That's not so. It's happened quite often. Then some quarries are located in protection zone. So you can see that this for the aquifer characterization, the value could range from 3 to 9. So in the end, it's quite easy. We can make a number, an index number, which can range from 12 to 144. This is the only simple value, but of course we have to translate this value into a kind of classification. That means how to translate a value into recommendation. That's the objective of the investigation. It's not to give a clear and complicated description, hydrogeological description of each site, but it's to give recommendation to the government. So in the end, based on case study and professional experiences, we say, okay, this is in green, this is a low interaction index. That means that if a quarry wants to start an exploitation, they just need hydrogeological characterization because the risk on the environment is not very important. If the interaction index is classified as medium, they need hydrogeological characterization and piezometric control. That means that the quarry has to drill few boreholes, a few piezometers around, just to have control of the seasonal fluctuation of the aquifer. The third level is high index of interaction. That means hydrogeological characterization, piezometric control, groundwater flow and transport model, but maybe with a basic calibration. And then if the index in interaction is very high, they need hydrogeological characterization, piezometric control, groundwater flow and transport model, but with much more information. That's what I call detailed calibration of the model. So, in conclusion, when anthropic activity is going to modify natural equilibrium, policymakers need first a list of simple but objective criteria, a clear and easily applicable methodology that helps to establish a classification. This classification could not be discussed by the different partners. The classification should help to decide which feasibility study action have to be taken. So I want also to insist here that a simple presentation of the result doesn't mean simple investigation and knowledge, because sometimes I think lots of methodology that was simple were applied without not enough information. I think drastic, it's an excellent example for the people who know drastic. I think it's a simple methodology, so lots of people use drastic without having enough knowledge and experiences, and so generally the methodology is not well used. So important simple presentation of result doesn't mean simple investigation and knowledge. So I think that sometimes the scientists must try to use, to develop useful methodology to translate science into practical advice, which can be easily used by the decision maker, which often are not specialized in our science. So also, this methodology could be used to assess various impacts of human activity as quarry, dump site, seveso industry, to groundwater resources in various environments, landscape, in town area, of course, for a sustainable development. So thank you for your attention. And if you have questions,
thank you very much.